Graphing logarithmic functions. The graph of a log function base a, when a is bigger than 1, looks like this. There's a vertical asymptote at the y-axis, and the graph approaches that asymptote down here, and then it comes up gradually like that. And then graph of a log function base a, where a is between 0 and 1, so like 1/2, 1/3, a small number, it looks like this one right here. It's useful to have these two graphs memorized, or just like to know the general shape of them. Now let's talk for a minute about why they look this way. So if you're looking at a log function base a, when a is bigger than 1, this is actually the inverse function to y equals a to the x, the exponential function when a is bigger than 1. And so we know that that exponential function looks like this. And we've obtained this log base a of x function by reflecting the exponential function over the line y equals x. So inverse functions, you get their graphs by reflecting over the line y equals x to get the inverse function's graph. So the graph of log base a of x actually comes from the graph of y equals a to the x. It's similar for this graph below. We reflect the graph of y equals a to the x for a is between 0 and -1, which looks like this. We reflect it over the line y equals x. Okay, let's do some examples. Graph y equals e to the x and y equals ln of x in the same coordinate plane. Now, before we get started, I actually know right away what the graph, like the shape of y equals ln of x is based on what we just talked about. So remember, natural log of x, that's the same as y equals log base e. And e is the number, it's like a number, right? It's about 2.71, and then the numbers after the decimal go on forever. And so this e is actually bigger than 1, which means that I know that the shape of this graph looks like that. Now, I'm not drawing it in a precise way. I'm just kind of like doing it approximately. Now, I know this because we have a log base a of x function, and we know that the shape of log base a of function for a is bigger than 1, it looks like this. So I'm using the fact that I've memorized this shape of the log function for a is bigger than 1 to just visualize what the natural log graph looks like. Now, if we want to know where a couple of exact points are, we can plug some numbers into x and then just like use our calculator to figure out where some of the exact points go. Now, there's another way to come up with a graph of natural log, and I'll show you. So let's just delete this. Okay, another way to do it is to graph the e to the x function. So we know we know sort of like the approximate shape of that. We know that it's something like this. And then we can find some exact points by plugging numbers into the e to the x function. So I'll make a little table over here. If I plug in x equals 0, I get e to the 0, which is 1. If I plug in x equals 1, I get e to the 1, which is about 2.7. If I plug in 2, I get e to the 2. Using a calculator, that's going to be about 7 point something. And so I can plot some points here. So I get the point 0, 1. We know 0, 1 is on all of these basic exponential functions. And then we get 1, 2.7 about. So 1, here's 2, 2.7 is about right there. And then we get, for when we plug in 2, we get about 7. So 7 is actually way up here off of our 7 point something, it's way up there. Okay, so we get this graph that looks like, this for e to the x. And that's a little bit more accurate than the one I originally did. Now, if we want to know what the graph of natural log of x looks like, we can actually use this graph as follows. So I can draw the y equals x line. Here's y equals x. And then I can actually reflect this y equals e to the x graph over this line. So if I reflect this, I get something. So this point right here is right here now. And this point that was at 1, 2.7 about is now going to be at 2.7, 1. So it's going to be now at like about 2.7, comma 1. So about right there. And so if I reflect every single point, I get something that looks like that, where this is the graph of y equals ln of x. Now this at the end is kind of curving down a little too much, so I'm going to fix it. So I'm using the graph of e to the x, reflecting it over the line y equals x to get the graph of y equals ln of x. And why do I reflect? Because e to the x and ln of x, they're inverse functions, and the graphs of inverse functions are obtained by reflecting over y equals x. Okay, let's do another example. Graph y equals log base 1/2 of x and y equals negative log base 1/2 of x in the same coordinate plane. So I'm going to start with y equals log base 1/2 of x. And I'm going to notice that the base here is a fraction. It is between 0 and 1. Now, using what we talked about earlier, I know that my graph is going to look like this one. I have that memorized. So I'm going to go back down to my picture and I'm going to think, okay, I know the graph looks something like this. It looks something like that. I just need to figure out where a couple of exact points are. How do I find out a couple of exact points? Well, what I can do is I can just make a little table so I can think, okay, if I plug in x value, like 1 into log base 1/2 of x, what do I get out? Now you're free to use a calculator to do this, or you can do it by hand. We know that log base anything of 1 is always 0. So we know that 1, 0 is always going to be on our log base a of x graphs. Now I'm going to pick 4 to plug in because I know that when I plug that into log base 1/2 of x, I get a nice number. So I'm skipping some of those other ones so that I can do this by hand. Now if I calculate what log base 1/2 of 4 is, how do I do that? Well, log base 1/2 of 4 is asking you, what is the output here? So what is y for log base 1/2 of 4? In other words, if I take 1/2 and raise it to the y power, like what does y have to be to get 4 out? Let's rewrite this a little bit. So 1/2 to the y is the same as 2 to the negative 1. And 4 is the same as 2 to the 2. And if I multiply this y times the negative 1, I'm going to get 2 times negative y equals 2 to the 2. This tells us that negative y has to be equal to 2. Right here, the bases are both 2, which means that the exponents also have to be equal to each other. This means that the output here, y has to be equal to negative 2. So if I plug in 4, I'm going to get negative 2 out. So I'm doing this by hand. It takes a little bit of time, but I'm finding an exact point on this graph by hand using my knowledge of logs. So I know 4, negative 2 is on this graph. Now, so that we can fit this in, I'm going to erase my work right here. Okay, so 4, negative 2 is on the graph. So I go over to 4, and then I go down to negative 2. So my graph's a little bit off. This light blue one that I sketched, it's a little off. I want it to actually look like this. It has its asymptote at the y-axis, and then it curves down like that and gradually goes out that way, going through the point 4, negative 2. Where there's an asymptote right here. Okay, so this one is log base 1/2 of x. Now I can actually use this graph to get negative log base 1/2 of x. So if I want to figure out now what is the graph of negative log base 1/2 of x, remember, putting a negative sign in front of a function like this reflects it over the x-axis. So this is going to reflect it over this x-axis here. So if we reflect this graph over the x-axis, we get something that looks like this. It comes up this way, and then this point at 4, 2 moves up here to, sorry, 4, negative 2 moves up here to 4, 2, and the reflection looks like that. So I'm using my transformation properties. Okay, let's look at a third example. Find an equation of the form y equals a log of x plus b for the transformed logarithmic function. So we're going to find an equation for this function. Now, we only have 2 transformations here. We have like an a and a b. So we only have to focus on those 2. Now remember, if you add a b inside here, that's a shift right or left. So this one here is a shift right or left. Now we know what the basic log functions look like. We know that our basic log functions, before they've had any transformations done to them, we know that they have an asymptote here at x equals 0. It looks like this graph that we're looking at, it looks like it has an asymptote here. So you can see there's an asymptote there. Now this asymptote has been shifted to the left by 3. This is actually going to tell us exactly what b is. This tells us that b has to be plus 3. So when you shift left, it's plus. So we know that b is equal to 3, looking at this asymptote and how far it's been shifted. How do we figure out what a is? One way you can figure out what a is you can use the fact that we know the equation is in the form a log of x plus 3, and then we can pick a specific point on this graph. So for example, notice that the graph goes through the point 0, negative 3, and we can actually plug the point into this equation and then solve for a. This will work because we only have 3 unknowns here, and if we know that a certain x and y should work in this equation, then that'll just leave us the a. So if I plug in negative 3 for y and 0 for x, and then I solve for a, I'm going to get a is equal to negative 3 over log of 3. So it's a little bit complicated, but that's what our a value is. So what we have here is a specific b and a specific a, and we can write out what our equation for this function is. So we now know that y is equal to negative 3 over log of 3 log of x plus 3. Now if I had used a different point on this graph to find a, I would get another equation, or like I'd get a slightly different expression right here, but it would, it's still a correct method.